In this video, I'm going to have a look at using the numeric Python library, numpy. So I'm going to open up my Spyder 6 IDE and I'm going to select File and Save As, go to Documents and create a new folder. Note if I call the folder numpy, I'm going to have a naming conflict, so I'll call it numpy tutorial and I'll just call the script file notes. So previously we've had a look at the directory of an object, and we've had a look at the object data model identifiers and discussed how everything in Python is an object and follows the object data model. So for example, we see the string class, it follows the object data model and it's got collection based identifiers as well as string specific identifiers. And then we've seen the numeric classes such as the integer, the boolean and the float. And then we've seen the collections such as the tuple, which is immutable, and the mutable list. So I've covered all these classes in a fair amount of detail in the previous videos. Just for a quick recap, what we're going to do is have a look at the following code. So what we have is two numbers, number 1 and number 2, and when we add them together, we perform integer addition. Now if we've got the two lists, fruits and fruits2, if we add them together, what we actually do is perform list concatenation. So when we've got lists of numbers, when we go ahead and add them together, we perform list concatenation. So in order to add the corresponding number from one list to another list, we essentially need to use a for loop, or we could do this a bit more elegantly using a list comprehension. So if we zip these two together, then we can get number 1 and number 2 from each of these collections, and we can add it together and form a list comprehension. So the data model method add essentially is defined to perform collection based behavior in a collection, or numeric based behavior in a number class. So the for loop works, but it's a bit cumbersome. What we essentially want is the numeric based behavior in a collection. So what we're going to do is import the numeric Python library using the alias np. And if we check its version, we see it's 2.1.1. So numpy is a third-party library and it's got a major, a minor and a patch version, so that's 2, 1 and 1 respectively. Numpy 2 has had a lot of changes over numpy 1, and this video is going to be applicable for numpy 2, so 2.1.1 or newer. So this third-party library also has a file. Now because I'm on Windows, the / is used to insert an escape character, but it's also the file separator used by the operating system. So the first / is an instruction to insert the escape character, and the second / is the escape character itself, the /. So if I print this out, the escape character is going to be processed, and I can copy and paste this file path into Windows Explorer. So we're in the lib and then in the site packages, and then we've got this numpy folder. And if we go in here, we've got this initialization Python script file. And this is the file that's referenced when you import numpy as np. And recall, you don't want your folder or any of your script files to be called numpy, as it will create a naming conflict. So if I go to Tools and Preferences and go to Variable Explorer, I can include the callables and functions, and I can view numpy in the Object Explorer. So we see it's got a huge number of identifiers. And if we type in np dot, we can see this list of identifiers. So we use the alias np, the 2-letter alias, because we commonly use functions from the numpy namespace, and it's just more convenient for np to be 2 letters opposed to 5. So if we have a look at the directory of np, we see a huge list of identifiers, and actually the character limit on the console is exceeded, so you don't actually see all the output. So I've essentially just asked ChatGPT to summarize the numpy namespace, and here is the results. So we've got a main class, the ndarray, and this is the main data structure that numpy library is based upon. And then we've got a number of data types that can be used in a ndarray. So they're essentially integer types, floating point number types, complex types, boolean types, string types, and then there's specialized types such as date time and time deltas. And there's a number of functions to create a ndarray. So essentially all of these functions are used to construct a ndarray. And the most commonly used function to construct a ndarray is the function array. So we've got essentially array attributes, and then we've got a number of mathematical and statistical functions, set operations, sorting operations, we've got random number generation, we've got linear algebra, input and output, and broadcast and vectorization. So if we have a look at the directory of the ndarray itself, once again we've got a large number of identifiers. So once again, if we ask ChatGPT to list these with a description, we see the object-based data model identifiers, and then we see we've essentially got the numeric operation identifiers. And we've got some casting operators, and then we've got our additional array attributes, and then some array manipulation methods, and then we've got some statistics and some sorting. Okay, so I'm going to create a new script, and I'm essentially going to use the old script as notes that I can refer back to. So if we import numpy as np, what I'm going to do is create this list hex strings. And then I'm going to join this together just to create one long Unicode string. And then I'm going to cast this into bytes. So I've got this bytes instance, and I can construct an ndarray from this bytes instance. So if we go to the bytes instance and have a look at the hex values, we can see this is similar to what we input earlier on. So now I'm going to use the ndarray class to directly cast this bytes instance into an ndarray. So notice that I've got the input arguments shape and buffer. So shape, I want it to be an 8 by 4. So this is going to be 8 rows by 4 columns. And I want the d type to be numpy.int32. So this means it's essentially using 32 bits, and it's int, so it's got negative and positive values. Okay, so now we've got the data type. Let's assign the buffer to b, and let's assign the result to mat1, and we can view this in the variable explorer. So Spyder automatically colors the background, so you can see the underlying pattern of the numeric values. So essentially we've got positive 0 to 16 at the top, and we've got negative 1 to negative 17 at the bottom. So if we go back to our list hex values and have a look at the second value, we see it's 0, 1 and then 6 zeros instead of 7 trailing zeros and 1. And this is because of the byte order used. So let's change the data type from integer 32 to unsigned integer 32, and this means it's going to only have positive values. So the first half of the array is essentially the same, and then instead of the negative values, we've got basically the maximum values. So you can see a difference between the two arrays when you compare mat1 to mat2. So the buffer used to create both arrays is the same, so it's the same bytes. However, a different data type is selected, integer 32 versus unsigned integer 32. So essentially the second half of the bytes in the array represent different values, and the first half are the same. Let's have a look at hex values 2, and once again we're going to create a bytes instance b2. So instead of having 8 hexadecimal characters, which is 4 bytes, we're going to have 16 hexadecimal characters, which is 8 bytes. So now instead of using integer 32 and unsigned integer 32, we're going to use integer 64 and unsigned integer 64. So now we can have a look at matrix 3 and also matrix 4. So now we see that the limits are much higher, and this is because we're essentially using twice as much memory for each integer. Now because we're using a 64-bit operating system, the default integer is the integer 64. So now that we have an array instance, we can have a look at its attributes, i.e. the properties of the array. So we can have a look at its data type, which is int32. We can have a look at its number of dimensions, which is 2. So we can also have a look at the length of the array. So this is essentially the length of the outer dimension. And this, recall, uses the built-ins double underscore len double underscore data model identifier. And this data model identifier controls the behavior of the built-ins function len. So that gives the 8, and this is the outside dimension. So if you think of this as a list of lists, it's got the dimension of the outer list. So we've also got the size of the array, which is essentially the number of elements in it. So this is 8 times 4, which is 32. And we can have a look at its shape, and this shows a shape tuple. So one thing to note is that a shape tuple is generally preferred, although Spyder displays the shape as size using a list in the variable explorer. So we've got item size, which essentially tells you the size of a single item and is essentially dependent on the data type. So we've got 4 bytes per value, and recall this is the 8 hexadecimal values that we've got in B for each value. And the number of bytes is essentially going to be the size times the item size. So we've got the casting method to bytes, and this gives us the bytes instance that we use to construct the array. We've also got the informal string representation, and when we print this out, we can see the array essentially as a list of lists. Note, if we cast this to a list, then we get a list of arrays. And if we have a look at the formal representation of the array, and let's just print this out, we can see that the formal representation actually instructs to construct an array using the array function. So if we have a look at the directory of numpy, we've got this array function. So although it displays array here, you think of it as np.array. So it's relatively rare to construct an array using the ndarray class directly with bytes instance in the form of a buffer. Instead, we use the numpy.array function and supply the data as a list, or a list of lists, or a list of lists of lists, depending on the number of dimensions of the array. We can also optionally assign the data type. So let me just instantiate a number of different arrays. So here I'm going to explicitly specify the data type. When I don't specify the data type, it's going to be inferred. So for example, if all your data is integers, it's going to be inferred as an integer. If one of your data points is a float, it's going to be inferred as a float. So int64 and float64 are the system defaults. And essentially, if you use the built-ins data types, int or float, these are recognized by numpy as int64 and float64 respectively. More commonly, an array would just be instantiated in the following manner. So notice that mat10 has the data type float64 and mat9 has the data type int64. The numpy function fromBuffer can be used to instantiate a 1D array from a bytes instance. So a 1D array has a lot in common with a list. So notice that it's essentially displayed in the variable explorer as a row, but when you open it up, it's displayed as a column. So a 1D array isn't strictly a column or a row. If we use the array method to list, we can cast it to a list. And notice that the list essentially has the same behavior. So we can see even more consistent behavior between the 1D ND array and the list. So let me just clear up my namespace and open up the ND array and the list side by side. So we can have a look at some of the properties of the ND array. So the ND array vector, it's going to have the attribute number of dimensions, and in this case it should be 1 because it's a one-dimensional array. And if we have a look at its shape tuple is going to be 16 comma because it's got 16 elements over that one dimension. And its data type is going to be integer 64. So this is numpy.integer64. So notice we can index into active using the index 0, and we can also index into vector using the index 0. So we've got consistent behavior when it comes to indexing. So we can also use the colon. And if we don't specify the start and stop around the colon, we're going to select all the values. And this is the same for the list and the vector. So in NumPy, dimensionality is important, and sometimes you need to actually explicitly specify a column or a row. So if we have a look at the size of the vector, we see that it's 16. And what I'm essentially going to do is I'm going to create a column from this vector by reshaping it into dimensions of 16 rows by one column. So if we have a look at the collapsed view of the variable explorer, we can see column size 16,1 and vector size 16. And if we have a look at the values, we can see that every single value is enclosed in its own set of square brackets, and there's an outer set of square brackets. So we can also explicitly resize this to a row vector. So this is going to consist of one row by 16 columns. And now we see in the collapsed view of the variable explorer that it's 1 by 16, and we can see that it's essentially got two outer square brackets. And when it's opened up in the expanded view, we can clearly see that this is a row. So we can have a look at the column.shape and the row.shape. So 16 by 1 and 1 by 16. And instead of using this vector.size attribute, what we can actually do is just tell it to use -1, which is essentially going to be all of the elements. So let me just delete the old column and row and recreate these, and we see we essentially have the same as what we had earlier. So let's delete these again. And this time, instead of using reshape, what we're actually going to do is we're going to index into the vector. And instead of -1, we're going to use the colon for all elements, and then we're going to create a new axis. So this code is a bit more readable because it's obvious that you're going to create a new axis here. So NumPy 2 documentation generally prefers this way to create the column and the row respectively. The NumPy function numpy.squeeze will squeeze this extra set of brackets. So this will essentially return the vector from the column or the row. The transpose essentially swaps the columns with the rows. So a row vector can be transposed into a column vector, and a column vector can be transposed into a row vector. And this is done with the attribute uppercase T. So the method swap axis will also do the same thing. So we can explicitly swap axis 0 with axis 1. And this essentially transposes the row into a column. So the NumPy function expand dimensions can be used to expand a vector over axis 1 to get a column, or over axis 0 to get a row. So I realize I've just made a mistake here. Let me just rectify it. So this should be 1 and 0. And now this works as expected. So let me just exit to clear out the namespace and then import numpy as np so I can access the numpy namespace. So we can create this vector using the function numpy.array. If we specify the minimum number of dimensions as 2, this is going to create a row. And we can transpose this row to get a column. So this is another way of creating a row or a column. However, it's generally preferred to use numpy.newAxis because the code is a bit more readable. So let's now create a matrix. So I'm just going to create this simple matrix, matrix 1, and it's going to have the values 1, 2, 3, and then 4, 5, 6. And if I go back to the identifiers in the NumPy library, notice that we've got this empty, like, 0, like, 1's, like, and full, like. So these essentially use the existing array as a prototype and get the dimensions from this prototype. So the values in this array are essentially random and are whatever was left in your RAM previous to making this array. So we've got a similar NumPy function, zeros like, and instead of using the input parameter prototype, it uses the input parameter A, where A stands for the array. So notice that these are all 0, and it's an array of integer 64. So we've also got numpy.ones like, and these all have a constant value of 1, and it's integer 64 as well. We could specify this data type as integer 64 using the optional parameter data type. Or we could override it to float 64 if we wanted a floating point number. So this gives 1.0 instead of 1, essentially casting the integer 1 to 1.0. So we've also got full like, and here we've got the array, and then we've got a fill value. And this fill value is 2, and this fill value was the integer 2. If I update this to the floating point number 2, for some reason it's still integer 64, but I can override this using the dtype of float64. So far we've only had a look at an ndarray that is either 1 dimension or 2 dimensions. We can actually have arrays that have a much larger number of dimensions. And I'm just going to use Excel to visualize this. So essentially we've got a 1D array which we can conceptualize as a column. Then what we can do is we can expand this to 2 dimensions. And we can conceptualize this as a number of columns being expanded over the additional dimension. And in Excel, you've essentially got sheets and you've got books. So we can think of each of these as a separate page in the book. So that's another dimension. Now what we can actually do is we can create multiple books. And then for these multiple books, we can put them in a folder. So let's just call this folder shelf 0. So all these books are lying on this shelf, but we can have multiple shelves. So now we've got shelf 1 and shelf 0, and we've got shelf 2, and we can group these together into a wardrobe, so a wardrobe of shelves. And then we can also have a group of wardrobes, and we can just call this a library. And then we could also group the library. So let's just call this library 0, and let's just make a copy of this library and call it library 1. We could just group this together and let's just call this a group. So you could keep going up dimensions, essentially using a parent folder. So what I'm going to do now is I'm going to go to pictures and I'm going to open up a picture in Paint. And notice that it's essentially got pixels, so this is like X and Y values, so columns and rows. And if we use the color picker, we can see that each pixel has a red, green and blue value. So your computer screen is essentially a large matrix of red, green, blue LEDs, and they have values from 0 to 255 each. And a pictures file essentially just tells you the numeric values of each of these. So if we just have a look, for example, at the corner of a file, we've got the red values, the green values, and the blue values. So you're going to essentially have a sheet of red values, a sheet of green values, and a sheet of blue values. So you can conceptualize a video as essentially being a folder of images, and each image is essentially an Excel worksheet with a red, green, and blue sheet. So if we open up a video, we can see that each frame has the same number of rows and the same number of columns, and each image is color, so it's got a red, a green, and a blue sheet. So essentially every time you're interacting with something on your screen, you're actually interacting with a data structure that's similar to ndarray. And generally every value in this ndarray is an 8-bit integer, because this gives us essentially the number of levels that the human eye can recognize for each color channel. Okay, so let's import numpy as np, and now let's have a look at creating arrays of different dimensions. So we've got a vector, and this is a 1D ND array. And we've got a matrix, and this is a 2D ND array. So notice that we've got two sets of brackets here, and we've got one set of brackets here. Okay, so if we have a look at this matrix, what I'm going to do is create two other matrices that have the same shape, so 2 by 2. So this is going to be matrix 2 and matrix 3, and let me just update the values so that these are different. So we've got 3 2D arrays, 3 matrices that each have the same shape. And we want to essentially combine these together into a 3D array. So we can just use numpy array and then create a list of these 3 arrays. And notice that we've got the 3D array book. And if we have a look at the index here, we've got 0, 1 and 2. So we've got page 0, page 1 and page 2. So we've got 3 pages, and we go from 0 to 3, inclusive of 0 and exclusive of 3. So if we have a look at book in IPython console, we can see how to construct this directly. And notice that we've essentially got 3 sets of brackets. And we've essentially matched the form of the formal representation. So notice that there is additional spacing here to distinguish each page in this 3D array. And then there's also spacing in front of the numeric values just to align them. So I've just noticed that I've not added a space here. So let me just fix this. So now everything's aligned as it should be. And let's actually create book 1 now. And let's go ahead and create book 2 and book 3. And let me just update the values. So now what we essentially want to do is create a shelf of books. So we can just do numpy array, and then we can have book 1, book 2 and book 3. And this gives us a 4D array. So now let's have a look at shelf in the IPython console. So notice that there's essentially 4 sets of brackets now. And if we have a look at spacing, we see there's essentially 2 blank spaces to separate out each book, and then there's 1 blank space to separate out each page in the book. So let's now have a look at the shape of each of these arrays, and specifically I want to focus on the column. So if we want to determine the number of columns in the vector, then we can have a look at the vector shape, and then it's going to be index 0. Now if we want the number of columns in the matrix, we can have a look at the matrix's shape, and it's going to be index 1. And if we have a look at the book shape, we can see if we want the number of columns, it's going to be index 2. And if we have a look at the shelf shape and we want the number of columns, it's going to be index number 3. Now if we want to have a look at the rows, it's going to be index 1 plus 1, index 2 plus 1, and index 3 plus 1. So this is going to be 2, 3, and 4. So we've approached this from left to right. But if we approach from right to left, we're going to have consistent values. So if we use the negative index, -1, notice the column is always going to be -1, and the row is always going to be -2 where there is a row. So when we use the negative index, we get the same results. However, the negative index is consistent, so we've always got -1 being the column and -2 being the row. So let's just create a simple book. And we're going to have book is numpy.array, and then we're going to have 3 sets of brackets. And then let's create the first page. And then let's add a space and move on to the next page. So this is going to be 2 sets of brackets here, because this is a page, and then another space, and then 2 sets of brackets for the third page. And then we're going to need the last bracket to close. So there's going to be 3 brackets at the end and 3 brackets at the start. So here we've got our book, and we've got index 0, 1, and 2. So we can use book.flat to create essentially a forward iterator. And because this is an iterator, we can use next on it to view each value one at a time. So essentially it flattens out the array. So book.flat is actually a view of the numpy array. So if we assign this to an array with the same number of elements, a flattened array with the same number of elements, we can actually replace the values. So notice that we're starting at 0 instead of 1 now in the elements, but the shape of book remains the same. So the function ravel will unravel the array, returning a 1D array that's essentially flattened. This is also available as a method. So if we have a look at its documentation, the method will tell you to refer to the function. And the function has the order parameter, and it can be C, F, A, or K. So C actually means the programming language C and has nothing to do with columns. So by default, the order of Python matches C. But we could change this to F, which matches the Fortran programming language. So here we've got 0, and then we move to the next page, and then we've got 4, and then 8. And then we move over to the next element here. So we've got 2, and then 6, and then 10. And then we've got 1, 5, and then 9. And then we've got 3, 7, and 11. So let's cast the book to a list. So this essentially gives us a list of each of the pages. So let's just think of this as a page list. Let me just rename this page list. And now let's have a look at the method toList. So instead of just the outer array being a list, now the entire data structure is essentially lists of nested lists. And this is the same type of data structure that you use with the numpy array function to instantiate a ndarray. So let's have a look at the book shape. So it's 3 by 2 by 2, so 3 pages by 2 rows by 2 columns. And if we have a look at its size, it's 12 because there's 12 elements. So we can actually use the reshape function to reshape the array to another shape that has 12 elements. So for example, we can reshape this into a 4 by 3 matrix, so 4 rows by 3 columns. So essentially this flattens it out and then it repopulates the new shape using all of the elements. Reshape is also available as a ndarray method. And notice that the order of the array is still maintained. We had the element 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 and 11, and this order is still retained. Okay, so let's have a look at book list, and if we index into essentially page 2, we can have a look at this page and we've got a list of lists. So now we can select row 0 and then we can select column 1. So this gives us the element 9. Now if we do the same for the ND array, so we've got a 3D array and we can select page 2 and this gives us a 2D array, and then we can select row 0 from this 2D array and this gives us a 1D array, and then we can select essentially column 1 from this 1D array to get the scalar value. So for convenience, because this is a single data structure, we can combine this all together. Book list, on the other hand, is essentially nested lists, so we need to access each inner list individually, and so we can't combine the brackets in the same way that we've seen before. And recall that we can use a colon when indexing to get a slice. Let's have a look at the function numpy.indices. So this essentially gives you the indices that you can use to access each value in the order as you go along the array. So for this point 0, it's going to be page 0, row 0, and column 0. And then for this next point 1, it's going to be page 0, row 0, and then column 1. And this essentially tells you how to go through the array using the indices. So we can use the array function reshape to reshape this 3D array into another 3D array that has the same number of elements. Let's have a look at swapping the axis. So if we swap axis 0 for 1, what we can do is now open this up in the variable explorer. So by default, the view is going to be axis 0. So if we change the original array to axis 1, we now see that this is axis 0. And if we have a look at axis 1 in the axis swapped array, we can see that this is axis 0 of the original array. So axis 0 and 1 are swapped as expected. Okay, so what I'm going to do now is have a look at the shape. So we've got the shape of the book, and I'm actually going to cast it into a deque. And I can use the append left method to append a new dimension. So essentially I want a shelf of 4 books. Okay, and I want every single value in this shelf to be 0. So I'm going to use numpy.zeros and then just provide the shape. So let me just view this in the IPython console and we can see all the zeros. So now I want to essentially update the first book. So I can index into the first book and then just replace this with book. So the first book now has the values of books, and then we've got 3 0 books after that. So we indexed into book 0 and then we specified all rows and all columns. Let's have a look at a simpler example now. So what we're going to do is we're going to create page 0 using the following 2D array. And then we're going to create page 1 and page 2. And let's just change the values so these are all unique. So we've seen that we can essentially create the book using numpy.array and then specifying a list of each of the pages. So let's go ahead and delete this book. And instead of using numpy.array, we can use numpy.stack. And essentially we're going to stack each of the pages. So this essentially carries out the same thing, but the code is slightly more readable. It's more obvious what you're doing here. We can also go ahead and split this array, and notice that we've split it into a list of each of the pages. So we could assign these to separate variables if we wanted. So let me just put this to page 0a, 1a, and 2a. Notice that each of these arrays are still three dimensions. So we can use the function numpy.squeeze to squeeze out this additional dimension of 1, which is 1 page. And this gives us the 2D array. So let me just save the script. So let me just save it as script 4. And then I'm going to create a new script. And I'm going to import numpy as np. And I'm going to have a look at the following lists, active 1 and active 2. And I'm going to go ahead and concatenate these. So now if we have a look at the following numeric arrays, and we essentially use the plus operator, then what we're actually going to do is perform the numeric operation. So the data model identifier add is configured for numeric operation in a numpy array. So the data model of the numpy array is essentially numeric based, but it is a collection, and sometimes we want this collection based behavior, and these are essentially available as additional functions in the numpy library. So for example, we've got numpy.concatenate, and we can use this to concatenate 2 different vectors. So if we also have a look at replication of a collection, recall that this is typically done using the multiplication operator. And in the case of a numpy array, the multiplication operator is going to be configured for numeric multiplication. So if we have a look, this is going to be times 3, the vector. So we've multiplied each value by 3. So if we essentially want to replicate it, what we do is we tile it. So we're going to tile this vector 3 times. And this gives similar behavior to the multiplication operator used in a collection. Okay, so I'm going to create a matrix, and it's going to have 2 rows by 3 columns. And now I'm going to create a row, and it's going to have one row by 3 columns. And I'm going to create a column, and it's going to have 2 rows by 1 column. So let's open these up in the Variable Explorer. And now notice that I can add the row to the matrix. So the row's been broadcast over every row of the matrix. So in other words, if we do this explicitly using numpy.tile, what we've essentially done is we've tiled it twice over its rows and just once over its columns. So in other words, it's broadcast to the matrix, so it's got 10, 20, 30 in row 0 and 10, 20, 30 in row 1. Now we can also broadcast a vector, and it's assumed to be a row and operates in the same way. The numpy function broadcast can be used to broadcast a row and a matrix, creating a broadcast object. So we can't view this broadcast object in the Variable Explorer, but essentially what we can do is use numpy.zeros with the broadcast shape to create this alt matrix. And then we can use flat. Recall that this gives a flattened view of the matrix. And because 2 arrays are broadcast, we've essentially got the position in each of these arrays. And we can use a list comprehension here. And we can broadcast a specific operator. In this case, we're broadcasting the add operator. So generally you won't want to do this because this is done behind the scenes when you use, for example, mat plus row. The numpy library also has the function broadcast to, so we can broadcast this row to the shape of the matrix. And here we see the result shown in the IPython console. So we can also use numpy.broadcast to broadcast a scalar to an array. So for example, if we broadcast the scalar 3 and once again use the shape of the matrix. So scalar 3 broadcast to the matrix is equal to, and I've just made a mistake here, I've used broadcast instead of broadcast 2. Let me just correct this. So now we see we've essentially got the scalar value 3 broadcast to the dimensions of the matrix. However, it's not very common to use broadcast to with a scalar. Instead, we would typically preference full like. So recall we've got the dimensions of the matrix, and the fill value is going to be the scalar here. Okay, so let's open up the matrix and the column, and now let's have a look at broadcasting the column. So if we type in matrix plus column, the column is going to be broadcast over the dimensions of the matrix, and then addition is going to be carried out. So this is the equivalent of tiling its row 1 time and its column 3 times. So if we have a look at the shape of the matrix, we see it's 2 by 3. And if we have a look at the shape of the row, it's 1 by 3. So let's squeeze this row and assign it to a variable. And we see it's got a shape of 3. So the last dimension matches. So this is why we can essentially broadcast a row in the form of a 1D ND array to a matrix. Now, if we do the same to the column, it goes from 2 by 1 to just 2. So if we have a look at its shape, we can see that its last element is 2, and the shape of the matrix's last element is 3. So if we attempt to use addition here, we're going to get the value error. Operands could not be broadcast together with the shapes. So in general, it's not really recommended to broadcast a 1D array to a matrix because it's not clear what dimension you're going to use. Your code is a bit more readable if you explicitly make it a row or a column. So in addition to tiling, we've got stacking. So we've got the horizontal stack and the vertical stack. So this essentially allows us to stack matrices horizontally or vertically. So when we stack horizontally, we're going to need a consistent number of rows in each matrix being stacked. And when we stack vertically, we're going to need a consistent number of columns in each matrix being stacked vertically. And we've already seen that we can also use stack, and this stacks the matrices over the next dimension, giving a book. So we can also use the numpy function hsplit to split an array horizontally by n. So you're going to have n equally sized arrays. So in this case, n is 3, so we've got 3 arrays in the output. And we can assign these to separate variables. So this is page 0, page 1, and page 2, respectively. And we've got the vertical split that we can use to vertically split an array. And once again, we're going to split this vstack into 3 arrays, giving page 0, page 1, and page 2. So hstack and vstack are essentially special cases of concatenation. We've also got the numpy function concatenate that can be used to concatenate a list of arrays over a specific dimension. So if we concatenate the matrix over axis 1, this recall is going to essentially expand the matrix over axis 1, so it's going to operate along the columns. And if we do it for axis 0, it's going to expand it along the rows. Now, as previously discussed, the new dimension is essentially left appended. So it's more convenient to use the negative axis. So axis -1 is always going to operate along the columns, and axis -2 is always going to operate along the rows. If we use axis equals none, then we essentially just flatten out the array and then perform the concatenation of the flattened arrays. Let's have a look at sorting an array. So I'm going to add negative and positive values here. And let's open up this array in the Variable Explorer. So if we have a look at the identifiers for the ND array, we see we've got sort, and sort is essentially consistent to the list method sort. So what it's going to do is it's going to sort the array in place over a specified axis. So essentially when I refresh this array, we can see that it's been mutated in place. So if we have a look at active 1 and we use sort, recall that this mutates active 1 in place as well. So the array method sort is consistent to essentially the list method sort. Let's return to the original array and instead use the numpy function sort. So this is immutable and returns a new array. So there can be a bit of confusion here if you don't realize that the sort method is essentially consistent to the list sort method and is mutable. So we've also got the array method argsort, and this returns the arguments over a specific axis. So here what it's essentially meaning is that we want to take index 3, which is -4, index 1, which is -2, index 0, which is 1, and index 2, which is 3, to sort this array. So if you indexed into the original array using these indexes, you would be able to sort it. So the numpy function takealong axis can essentially use these sorted arguments to sort an array along an axis. So here we've got the matrix, and then we've got the indices, and then the axis is going to be -1. So this is similar to using numpy.sort and then specifying the array and the axis -1. We've also got numpy.insert, and we can use this to insert a row or a column along an axis. So in this case, we're going to use axis -2, so we're going to insert a row, and we're going to insert it at 1, and we're going to insert the row 9999. So the ndarray doesn't have the method insert, so there's no method insert consistent to the list method insert. It's just available as a numpy function. Now, if we have a look at the following vector, 3, 4, 4, 7, 9, and then we have this other vector elements, 1, 2, 6, 6, 8, 10, 11, and 13. Notice that both of these are sorted. So we can use the numpy function insert sorted to search within the vector the locations that we would insert the elements, and we want the side of the new elements to be on the right hand side. So with these elements we can use numpy.insert, and we've got the vector, and then we've got the indices to insert each element at, and this gives us essentially the extended vector. So essentially all of these elements have been added to the vector, and notice that the extended vector is still sorted. So let me just exit to clear up the namespace a little, and let's recreate the matrix. And what I want to do is flip it from left to right. So here I can select all rows, and then I can reverse the columns, and this flips it from left to right. The numpy function flip left right will also do this, and it's a bit more readable. So essentially gives the same result. So instead of flipping left and right, we can flip up and down. So here we're going to essentially reverse the rows and index to all of the columns. And we've got the numpy function flip up down, which performs the same behavior but is a bit more readable. So flip left right and flip up down are specialized cases of flipping the matrix. So we've also got the numpy function flip, and we can use this to flip a matrix over a specific axis. This will also work for higher order arrays. The numpy function pad can also be used to pad an array. So here we've got a 2D array, which is a matrix. So the pad width is going to be a list of two tuples. So the first tuple is going to be the rows, and then the second tuple is going to be the columns. So this is essentially going to be the top and the bottom in the first tuple, and then the left and the right in the second tuple. So here we're going to have the mode as being constant and have a constant value of 0. So here, if we have a look at the rows, we can see we've got one row inserted at the top, two rows inserted at the bottom, and then at the columns, we've got 3 columns inserted to the left and 4 columns inserted to the right. And we can have a look at the documentation of the pad function to get more details about these input arguments. So if you don't want to pad by all the dimensions, then you just use 0. So in this case, we've just padded by 2 rows at the bottom. So by now you should be more or less familiar with the range object. So recall that it's got 3 input parameters: the start, the stop, and the step. And we're inclusive of the start and exclusive of the stop. So in this case, we're going from 0 to 16 in steps of 1, and this means the last value is going to be 15. Now the default step is 1 and the default start is 0, so we can also use this with 2 input parameters or 1 input parameter respectively. So if we import numpy as np, we have the numpy function arange, where A stands for array. So this is going to return an array. And once again, we've got the 3 parameters: start, stop, and step. And we've got the default value of 1 for step and a default value of 0 for start. The numpy array range function also has the optional parameter data type, so we can use this to change the data type, for example, from the default, which is going to be integer 64, to float 64. Notice that we can also use floating point number as a step. If we try this with the inbuilt range function, notice that we get a type error. So the numpy array range function is more flexible. Note, however, that we're still using 0 order indexing, so we're inclusive of the start bound and exclusive of the stop bound. So sometimes it's easier to input, for example, 0 to 16 plus 0.1 and a step of 0.1. So if we return to the array range of 16, because this outputs a numpy array, we can use the reshape method on it and we can get a matrix this way. So I want to address some potential conflicts when it comes to namespaces. So if we have a look at the following list, and if we import built-ins explicitly and type in built-ins dot, we can see all of the built-ins identifiers. Now, one of the problems is that some of the identifiers, such as absolute, all, any, min, max, and range, essentially have a counterpart in the numpy namespace. So any Python script file has access to built-ins automatically, but I'm going to implicitly import everything from built-ins so we can see it on the variable explorer. And if we have a look at numpy.all, we see a list of identifiers. So if we type in from numpy import star, what's essentially is going to happen is we're going to import all the identifiers from numpy and overwrite some built-ins identifiers which have the same name. So when NumPy was originally developed, scientists that were used to using MATLAB would use this type of import, and they would have naming conflicts. So for example, if we have a look at the minimum, the maximum of the archive, any of the archive, all of the archive, and absolute of the archive, notice that what's being returned is essentially a NumPy data type. If we exit and instead use the same functions, we're going to use the built-ins equivalent. So notice that we have slightly different behavior here, returning essentially built-ins data types. So in the past, to prevent this kind of conflict, the prefix a was used in front of the identifier. So instead of having range, you would have array range. Instead of having min, you would have array min. Unfortunately, this naming convention wasn't exactly consistent, and in general, Python developers discouraged academics and data scientists from using the star imports. So instead, you would have each namespace essentially compartmentalized. So you would access the identifiers from NumPy using the alias np. So therefore the a was typically dropped from the identifiers. So instead of using a max and a min, you would just use max and min. Unfortunately for array range, then the a hasn't been dropped, so you still have a difference here, and there's no range function in the NumPy namespace. So we've seen that when we use array range, we need to be careful when we're using stop bound, because we are exclusive of the stop bound. There's a related function called linear space, and here we've got the start and the stop value, and we're inclusive of both, and we can specify the number of data points. So under the hood, it calculates from the stop and the start, and the number of data points essentially calculates a step using float division, and then gives you the linear spaced values. Now notice that because it is using float division, that all the values returned are floats. So even though in this example all the numbers are integers, they are represented as a floating point of an integer. Now if we have a look at 10 to the power 1 and 10 to the power 8, we see we essentially get a 1 with a 1 0 behind it, and we get a 1 with 8 zeros behind it. So what we can do is we can create linear space values using these two limits, and we can set the number to be 8. So we've got the related function logspace, and here we've essentially got 10 to the power 1, 10 to the power 8, except we don't explicitly put 10 to the power here. And then we've got the number of data points to split out on the log space. So let me just save these as variables. And what I want to do is essentially use the variable explorer to plot these out. So we can see the linear space here, and we can see the log space here. So let me just modify some of the plot properties. So what we want to actually do is show the markers. So here we can see we've got the linear space markers. And here we can see we've got the logspace markers. So if we go back to the numpy array range function, and here what we want to do is use an integer step. So we want to go from 0 to 5 in steps of 1. So it's quite common to request such a range object in the form of a y column and an x row. And we've got the numpy object open grid that we can index into. So if I index into this, I'm selecting the rows 0 to 5 and the columns 0 to 5. I'm going to get the following row and column vector. So let me just change the number of columns requested. So this is actually going to change the row vector because it's got the number of columns. So let me just change the columns back to 0 to 5. And this is going to change the number of columns in this X row. Okay, so sometimes we won't want integer spaced values. So instead we use the linspace, and we use this with the numpy.newAxis. So let me just create the following X row and the Y column. And sometimes what we actually want to do is expand each of these into a matrix using the other array's dimensions. And we can do this using meshgrid. So essentially we've got this X row and we've duplicated it for every single row in the column. And then we've got this Y column that we've essentially duplicated for every column in the row. So notice that we've essentially got XY here instead of YX. And this is because of the default coordinate system used. If we change the indexing to IJ, then we get YX. And this is consistent to the open grid that we used earlier. So generally this is used to create XYZ data. So here we're going to create a function that's going to generate the Z data. So instead of defining and calling the function, quite often the function is assigned using a lambda expression. So this is essentially a one-line form of a function. So let me just comment out the function. So here we've got the function name. Instead of def, we're using assignment, and then we use the keyword lambda. Then we've got the input values, and then we've got the colon separating out the return value. So the colon, when used with a function, is used to start a code block, but because this is a one-line function, it's just used to separate the inputs from the return value. So with a lambda expression, it can be anonymous, so we don't assign it a function name. Instead, we just wrap the function around in parentheses, and then we can supply a second set of parentheses to provide the input arguments. And then we can assign the value to the variable Z matrix. And this gives the same matrix that we've seen before. So when we essentially used the lambda expression to create the Z data, we used a number of numeric methods in the ndarray. So these are essentially consistent with the integer and floating point number. And if we just create a new script, we can have a look at the following matrix. Matrix 1, numpy.range 16, and we can reshape it to be 4 by 4. And let's open this up in the variable explorer. And let's create a second matrix that has the same dimensions. So this one's going to have negative and positive values. And we can open this up in the Variable Explorer as well. So let's first look at a unitary function. So we've got the function numpy.absolute, and this is going to return a matrix of absolute values. So essentially it's going to strip the sign. So we can also use the built-ins function absolute on the matrix, and recall this is defined in the ndarray class using the data model method absolute. So we could essentially assign this to a variable if we wanted to. So we've also got the unitary operators positive and negative. So positive is basically going to multiply everything in the matrix by positive 1, and negative is going to essentially multiply everything in the matrix by -1. So this uses the data model identifiers, positive and negative respectively. So we've already seen this behavior when we looked at numeric data types in a previous video. So this should essentially be revision. So we've got the unitary operators, which essentially operate on one ndarray, and then we've also got the binary operators, which operate between two ndarray instances. So for example, when we're using add, we're calling the method from matrix 1 and we're applying it to matrix 2. So here we're going element by element and adding the respective values. So we've also got subtract, which is essentially going to be element by element subtraction. We've got multiplication, which is going to be element by element multiplication. We've got to the power of, which is essentially going to be element by element to the power of. So we can use all these numeric operators with an ndarray and a scalar, and essentially these follow the rules of broadcasting that we've previously examined. So we've also got essentially integer division. So this gives us the integer floor, and we've got the associated modulus. So you can see, for example, 0 remainder 0, 0 remainder 1, 1 remainder 0, 1 remainder 1. And recall that divmod essentially returns both of these in the form of a tuple. So we've also got the float division. And recall this is always going to return a floating point data type. So you'll see 0 point, so this integer 0 is represented using a floating point number. So if we have a look at the square root of matrix 2, notice that every single negative value displays not a number value. And this is because the data type currently used doesn't support complex numbers. So we can cast matrix 2 to the data type numpy.complex 128, so 128 bits used. And notice that when we use the square root of this, we get complex matrix. So here we've got j, which recall j squared represents -1. So we can have a look at the real and the imaginary attribute, which essentially gives the real numbers and then the prefix of the j. And we can have a look at the matrices complex conjugate, which essentially swaps the sign of the imaginary component. So the ndarray also has the method round, which can be used to round floating point numbers to a specified number of decimal places. So let me just create the following ndarray that's got values to 2 decimal places. And notice that I can use the round method, and if I don't specify any input parameters, it's going to round the floating point number to an integer. If I specify the decimals to 1, then I'm going to have 1 decimal place. So we've discussed data types briefly when we first introduced the ndarray, initializing from a bytes instance. So let me just create the following ndarray. So it's going to have the integers 1, 2, 3 and 4. And this time I'm going to specify the data type as numpy.unsigned integer, and it's going to have 8 bits. So the values are going to be from 0 to 256, inclusive of 0 and exclusive of 256. So notice that when we add 200, we get an array of values as expected. If we add 255, what actually happens is we roll over, and therefore we get 1, 2, and 3. And notice if we take away a negative number, all the values are going to be positive. So essentially we've rolled over in the opposite direction. Let's now have a look at using numpy integer 8. So this is going to have positive and negative values. So it's going to go from -128 to 128, and it's going to be inclusive of the lower bound and exclusive of the upper bound. So we can go ahead and add 100. Notice if we attempt to add 200, we're going to get this overflow error. So recall we've seen integer 8 arrays when we examined an image. So a value above 255 wouldn't make sense for the color property of a RGB LED on a screen. So that's why we restrict it to within a specific range. It also conserves memory. So we can also create an array of strings. So in this case, we've created an array of letters, and it's 4 bytes per letter. So here we see it's string 32. So we can go in here and replace the string. Notice that the string that we input is truncated. And this is essentially because the array is fixed to be 1 letter or less. So this behavior used to be similar in ndarray, where the value would be truncated. Now it instead shows this overflow exception error. But they haven't updated the behavior for essentially a Unicode array. So we can concatenate a Unicode string to the Unicode array. And notice that this is less than or equal to 6 Unicode characters. So let me just clear the namespace and create a new script. So what I'm going to do is create this numpy array, and it's going to have a lot of 0 values in it. So we can use the numpy.count non-zero values to count the number of values that are non-zero. So we've got 3 values in this array that are non-zero. We can also use numpy.nonzero to get the indexes of each of these values. So this is index 3, this is index 6, and this is index 9. So let's just assign that to a variable. And what I want to do now is index using these indexes. So this selects the values in the array at the specified indexes, i.e. in this case it's going to be the non-zero values 1, 2 and 1. We can use a comparison operator with an array, and notice this returns a boolean array. So we can check if each value in the array is equal to 0 or not equal to 0. So we can index with this boolean array, and this returns the array 1, 2, 1, i.e. the non-zero values. We could also check to see if the value is greater than 1, and there's only one value that's greater than 1, and that's the value 2. So let's create the array y, which is going to be 1, 2, 3, 4. And essentially, let's create a boolean mask. So we can index into y using this boolean mask. So we're just going to retrieve the values in the array that are true in the boolean mask. So this is going to be 1 and 2. And 3 and 4 have the corresponding values false, so they're not shown when we use this boolean mask. The numpy function where can be used to check for a condition and then give a set of instructions if the condition is true, and a set of instructions if the condition is false. So here we've got the string 0 and the string non-zero for 0 and non-zero values. So if we create the following array that has essentially complex numbers in it and some numbers that aren't complex, we can use the isReal identifier to see what indexes are consisting only of real values and what indexes have complex values. So this conditional logic can be applied to higher dimensions. So let's create this matrix 1, and let's just create matrix 2, which is going to be the negative of matrix 1. So let's create a selection mask, and let's just use numpy.zeros, and the shape's going to be 5 by 4. And essentially everywhere we've got a 0 value is going to be false. So let me just update one section of this selection mask to have true values. So this selection mask is of the data type float 64. Let's just change its data type to integer 64. It should work in both cases. We could also directly change it to a boolean data type if we preferred it to explicitly say true and false. So now that we've got this selection mask, we can use numpy.choose, and we can use this selection mask to choose a value from either matrix 1 or matrix 2. So essentially, if the value in selection mask is 0, which is false, we're going to take the positive value from matrix 1, and if the value is 1 or true, then we're going to take the value from matrix 2, which is negative. So previously when we had a look through collections, we've seen the set collection, and the set collection essentially gives a collection of unique values and is unordered. So it doesn't have a numeric index. For a numpy array, you're essentially wanting set-like behavior of an array that's numeric. So if we create this array x, we can use the numpy function unique to return the unique values in x. So this is a numpy array and it will have a numeric index. So the numpy library has a number of functions that have 1D in them, which means they essentially only work with a 1D array. So for example, there's in 1D, which can be used to check to see if a value is in a 1D array. So in this specific case, this is deprecated, and this function is expanded to multiple dimensions. So here we see that 1 is in the second array, 2 is in the second array, 3 is not in the second array, and 6 is not in the second array. So if we have a look at the union between both sets, recall that we used the OR operator here. We've also got the numpy function union 1D, which essentially performs the same operation using 1D ND arrays. So we've got the other set operations, such as the AND, which will give you the intersection, i.e. the values that occur in both sets or in both 1D and ND arrays. And then we also have the difference, and this is essentially the values that are in the first set that aren't in the second set. And then we've got the exclusive OR values. So this is essentially the values that are in the first set or in the second set, but aren't in both sets. So when we had a look at the numpy function isin, because we get a boolean array, we can invert it. So if we just use tilde to invert it, notice that all the values that are true are now false, and vice versa. This is actually using the bitwise operator. I'm not going to delve too much into the bitwise operators here, but we've covered them previously when we looked at the built-in numeric data types. Let me instantiate the following list W. So it's going to consist only of numeric values. And recall we can use the built-in functions to determine the maximum value in the list, the minimum value in the list, the sum of all the values in the list. We can have a look to see if any of the values in the list are true. So all non-zero values are true, and we can see if all of the values in this array are true, and we see that they are. So let's now update W to be a numpy array. And notice that we've got the numpy functions, max, min, sum, any, and all. And these operate pretty consistently for this 1D ND array. All of these numpy functions are available as array methods. So we've got max, min, sum, any, and all. Okay, so let's open up the array in the variable explorer. And to the left hand side, we're going to see the numeric index. So if we have a look at the argument max, we're going to return the index of the maximum value. And if we have a look at argument min, we're going to return the index of the minimum value. In addition to sum, we can have a look at the cumulative sum. So this is going to be 0.4 and then 0.4 plus 1.2 and then 0.4 plus 1.2 plus 1.3 and so on. So the shape of the cumulative sum is going to be the same as the shape of W. We can also get the mean value of W, and this is essentially the sum divided by the shape, and it's going to be the 0th dimension of the shape, because this is 1D ndarray. So we can have a look at the variance, and here we need to input the delta degrees of freedom. So if we just manually calculate this, what we are doing is we are taking the mean away from W, and then we're going ahead and squaring this, and then we're taking the sum of this, and then we're essentially going to divide it by the number of data points. Now, because we're using the delta degrees of freedom, we're going to subtract this by -1. And this gives us the same variance as before. So the variance is less commonly used because it returns essentially squared units. We generally take the square root of this to get the standard deviation. So the mean and the standard deviation are quite often used to describe a set of measurements. So we've also got the product, and this essentially multiplies each value in the array. And we've got the cumulative product, which does this along the array. So once again, maintaining the shape of the array. So similar to the cumulative sum, but you're calculating the product instead of the sum. The numpy function clip will clip an array to essentially a minimum and an upper bound. So notice that all the values lower than 3 are now replaced with 3, and all of the values higher than 8 are replaced with the value 8. So the identifier peak to peak will essentially take the maximum value and subtract the minimum value from it. So for example, if we have a look at the maximum value of 9.9 and the minimum value of 0.4, peak to peak is essentially going to give the difference of these. Okay, so since peak to peak is less commonly used, it's not available as an array method anymore, and is only available as a numpy function. So if we go ahead and use this, we're going to get the value 9.5 as expected. Let me just create the following array x. So it's going to have the values 1, 2, 3, and 4. And what I want to do is essentially explore the concept of any and all. So if I have a look at numpy.anyx, I can see that this is true. And if I have a look at numpy.allx, I can see this is true. If I replace one of the values by 0, we can see that any is still true, but all is not. And if I replace all the values by 0, we can see any and all are both false. So in other words, any means are any of the values true, and all means are all of the values true. So for convenience, we just demonstrated the statistical functions using a 1D array. We can also apply these to higher dimension arrays, and we essentially have the parameter axis. So recall that axis of -1 means we're going to be operating along the column axis. So if we have a look at the maximum values, we've essentially got the maximum values for each row. So we've got 9, 12, and then 9. And if we use the optional parameter, keep dimensions, and set it to true, we can see we get a column. And if we switch to axis -2, this means we're going to be operating along the rows. So this is essentially going to give us the maximum value in each column. If we select axis equals none, we essentially flatten the array and then retrieve the maximum value in the entire array. And this is the default behavior of the statistical function when no axis is provided. We can also retrieve the index of the maximum values using the argument max function. So this is essentially going to be row 0, and then row 2. So we can index into the matrix using 0, 1, and 2 and these provided indexes. So this retrieves the maximum values. Consistent if we had just used the max method with axis equals -1. So most of the additional statistics are slightly less commonly used and are just available as numpy functions. So let's create the following arrays, x1 and x2. And we want to have a look at the covariance between these two arrays. So notice that we get this matrix. So let me just manually calculate out the covariance between x1 and x2. So we're essentially summing the difference of x1 from its mean, multiplied by x2 from its mean, and I'm multiplying these together, and we're dividing by the shape of the array and using delta degrees of freedom of -1. So notice that gives 5, and that shows the two values on the diagonal. The other values are essentially the variance of x1 and the variance of x2. So that's why you get this array. And because the formula used to calculate the covariance is symmetrical, the two values of 5 are the same. Let's have a look at the difference. So this is essentially going to calculate the difference as you propagate along an axis of the array. So let's just assign this to the variable d. And what we've done here is we've done 3 minus 9, which is -6, and then 5 minus 3, which is 2, and then 6 minus 5, which is 1. So if we have a look at d2 and we once again have a look at the difference, but this time we want to have a look at the difference of d. Notice that what we've essentially done is we've done 2 minus 6, which is 8, and then we've done 1 minus 2, which is -1. So we can do this directly by specifying the additional parameter n, so number of times to calculate the difference, and we get consistent results as expected. So let me create the following array y, which has duplicate values. So we can get the unique values by using the numpy function unique, and we can count the occurrences of these unique values by using the numpy function bin count. So if we have a look at the two arrays, unique y and bin count y, side by side, we can see the unique values ny, and we can see the counts for each of these values. So 0 occurs 1 time, 1 occurs 3 times, 2 occurs 2 times, and 3 occurs 1 time. So this is similar in behavior to a counter. Recall that a counter is essentially a dictionary subclass, and here it's ordered by the most occurring value to the least occurring value. So let's have a look at the numpy array Z. So it's essentially going to be ordered. So we've got 0 3 times, 1 3 times, 2 4 times, 3 2 times, and 4 2 times. So we can use the numpy function median to get the median value. So this is essentially the value in the middle of the array. So notice that it's 2.0 because it basically averages the two middle values. And even if we make the array an odd number of elements, it still averages this and returns a float. So we've also got the mean, and generally the mean and the median should be similar. The median is less susceptible to large outliers. So the numpy function average behaves similarly to the mean, and it assumes that there's a weight of 1 for each of the values. So we can use the numpy function onceLike to create an array of weights that's uniform, so 1 for each value. So what we can do is just implicitly specify these weights. So we get the same value that we get with the average function without the weight specified, or when we calculate the mean using the mean function. So if we index into weights, so if we index into index 3 and assign it to 1000, then essentially it means this value is going to occur 1000 times instead of 1 time. And then there's 2 additional ones beside it. So one's going to occur 1002 times. So now if we use the average function with these weights, the average value is going to be much closer to 1 because most of the values in the array are going to be 1. So if we go back to our array W, we can use the numpy function quantile to generate quantiles. So here we specify the array and then we specify the quantiles. So generally this is going to be 0, 0.25, 0.5, 0.75 and 1. So we're essentially getting the lower and upper boundary to get the first quarter, the second quarter, the third quarter and the fourth quarter. And the value in the middle should be the median value. So the default behavior of a quantile will essentially split it into 4. We could also optionally split it into 5. So using increments of 0.2 instead of 0.25. We also have the numpy function percentile. And this essentially is similar to quantile, but we use a percent here instead of a normalized float. So basically if we times this by 100, we'll once again get the same boundaries for 25% of the values to lie between the specific range. Let's have a look at creating W2, and this is going to be a function of W. So we can use the numpy function to correlate W with W2. So a bit more details about the correlation function can be seen by examining its docstring. So essentially it just retrieves a correlation value. And because W2 is a function of W, it's going to have a relatively high correlation value. What we can do is just index into W2 and change one of the values. So here we notice that the correlation value changes. So instead of using the correlation value, it's often more popular to use the correlation coefficient. Because the correlation coefficient is essentially normalized. So let's return to W2 and let's calculate the correlation coefficient between W and W2. So notice in this case we've essentially got a 2x2 array of 1, 1, 1 and 1. So a value will perfectly correlate with itself. And then here we're looking at the correlation of W with respect to W2 and then W2 with respect to W. And these values are the same because the correlation of W with respect to W2 is the same as the correlation of W2 with respect to W. So the formula's got some symmetry. So here we see when we update one of the values in W2 to essentially make it less correlated, it moves away from 1, and then when it's essentially not correlated at all, it's close to 0, and if it was inversely correlated, it would go to -1. Okay, so I'm going to create the array x and y, and I'm going to calculate the dot product. So this is essentially element by element multiplication and then summed. So 1 times 0 plus 2 times 1 plus 3 times 0.5. Now, if I do numpy.correlate x and y, I essentially get the same as the dot product. So the correlate function has the additional parameter mode, which is set to valid by default. So this essentially gives the same as the dot product. If we set the mode to be the same, it's going to return an array that's got the same dimensions as the starting arrays. And if we use the mode of full, we're going to have a full correlation. So the correlate function is essentially a more specialized scientific or engineering function, and its use goes more towards scientific Python. Let's have a look at the identifiers in numpy that come from the math module. So we've got pi, which is essentially the circle constant or half the circle constant. The circle constant is generally 2 times pi, which is also known as tau. So tau is essentially the circle circumference divided by the radius. We've also got infinity. So for example, if you divide by 0, you're going to return infinity. And we've got not a number. So for example, if you instantiate an array using a specified data type and then provide data that's non-numeric, it'll be represented as not a number. So for some of the other constants, we're going to need a factorial. So essentially the factorial of 1 is 1, the factorial of 2 is 1 times 2, which is 2, the factorial of 3 is 1 times 2 times 3, which is 6. And the factorial of 4 is 1 times 2 times 3 times 4, which is 24. Okay, so now that we've got the factorial, we're going to use this in a series expansion. And the default number of terms is going to be 1000. So we want to return the sum of 1 divided by the factorial of n for n in the range of terms. Okay, so if we have a look at the series expansion of 1, we get 1. We change this to a higher number, 10, we get this 2.718 number, and notice that the higher number of terms that we use, this number begins to converge, and it converges to E, which is known as Euler's number. So if we look at another series expansion, here we're going to just have a slightly different term. So if we just examine this series expansion 2, and we have a look at 1, we've got 1.0. If we have a look at 2, we can see the values decreasing. And if we change this to 10, 100, and 1000, we can once again see that the number begins to converge. And this converges to the Euler gamma number. So E and Euler gamma are both available as constants. And we can essentially use these constants with the array functions. So for example, if we use the full function, we can create an array that's the shape of 4 by 2, and it's going to have infinite values. So let's have a look at defining our own function here. So here we're going to define the function cube root, and it's going to return the cube root of a number. So here we can calculate the cube root of 1, of 3, and of 27. So if we want to calculate the cube root of all of these numbers, we can map the cube root function to a list. And then to see all of the values, we can cast this map function into a list. So the numpy function vectorize is similar, and it can be used to vectorize a function with a ndarray. So here we've now got the vectorized function numpy croot, and we can supply a numpy array. So if we import the math module and have a look at the math module identifiers, we see we've got a large number of functions here. And essentially all of these functions are vectorized. So for example, if we have a look at the square root of 4, we can see that these functions behave similarly, except there's a slightly different data type. So one's going to give the float 2.0, and the other is going to give the numpy float 64 d type, that's also 2.0. So notice that the numpy function is already vectorized, so we can supply a numpy array to it, and this allows us to use the square root function along the array element by element. And because it operates element by element, it will also apply to higher dimensional arrays. So for example, we can use it with the matrix. The exponential function will calculate the exponential value of a floating point input. So notice that when the value is 1, we essentially get the base, which is numpy.e. So if we have the following linear space values and plot them, we see we've essentially got a straight line. If we take the exponential of these values and plot this out, we can see that the line exponentially increases. And the logarithmic function essentially does the inverse of the exponential function. Notice that one of the values here is minus infinity because the log of 0 is minus infinity. If we plot this out, we can see that it's essentially done the opposite behavior of the exponential function. So if we take the log of the exponential, we should return to the original starting values. And if we plot this out, we can see we've essentially got the original values. So the exponential and the log are to the base e, which is the natural base. We also use base 10 quite a lot, which is decimal. So let me just clear up the namespace and let's have a look at the base 10. So let's create this array x, and it's going to have 10 to the power for the power in the range of 0 to 6. So here you can essentially see the number of zeros behind the value matches the index. So the numpy function log10 essentially does the opposite of this, and we return back to the powers, so 0, 1, 2, 3, 4, and 5. So if we calculate tau as being 2 times numpy.pi, what we can do is create linear space values of x. So here we're going to go from 0 to 360 degrees. And as humans, we're quite used to working in degrees. The natural unit for trigonometry is, however, radians. So we can use the numpy function degrees to radians to cast 2 radians. So manually, this is essentially multiplying it by tau and dividing it by 360. So here we can see that x2 is unchanged. So we've also got the reverse function, which is going to be radians 2 degrees. And here we can see that x is unchanged. So what this does is it multiplies it by 360 and divides it by tau, and multiplies this by the original array. Okay, so what I'm going to do is essentially use linspace directly with radians instead of starting from degrees. So let's just have x going from 0 to 2 times numpy.pi, which is tau. And I've assigned tau earlier. And now I can use the trigonometry functions, sine, cos, and tan on these x values to essentially return y values. So here we can view the sine plot, the cosine plot, and the tan plot just using the variable explorer. So the axis shown here is going to be the index, so we've got 100 data points. So we see that the cosine is a delayed sine, and we see that the tan is discontinuous. So it would go from positive infinity to minus infinity if we had infinite data points. We've only got 100 data points, so that's why it doesn't go as massively high or massively low. So there's also the arcsine, arccosine, and arctangent functions, and these have a slightly different range that they operate over. So once again, we can view these in the variable explorer and plot these just to see what the functions look like. So the numpy library has its own random module which compartmentalizes functions related to random number generation. So the numpy module random should not be confused with the standard module random, which also compartmentalizes functions related to random number generation. So the identifiers in the standard module random typically return a scalar, and identifiers in the numpy random module typically return a numpy array. So typically you would import the standard module random and then access its identifiers by typing in random dot. And for numpy you would import numpy as np and access its identifiers by typing in numpy.random dot. Now unfortunately the identifiers don't display in the script editor. There's a bit of a bug here that's going to be addressed in future versions of Spyder. These identifiers display in the IPython console, and I can have a look at the directory numpy.random and ask ChatGPT for more details about each of the identifiers. Okay, so the random numbers generated are pseudo-random, and one thing that we can set is the seed. So this essentially sets a random state, and if we restart the kernel and go back to this random state, our code is going to be reproducible, so we're going to get the same random values. So in general we set an integer here, so for example I can use 66, and let me just create the following vector, and what I'm going to do is I'm going to use the permutation function, and here I'm basically going to get a random permutation of the vector. So if I run the script file again with the same random seed, notice I get the same permutation. If I change the numeric value of the seed and run this again, notice I get a different permutation. So the function choice can be used to select a random choice from the numpy array. So in this case we've got 8, 10 and 10 again. The shuffle function will shuffle an array in place. So notice it's got no return value, and the array is updated in place, so this is mutable. So if we go back to the choice function, we can also specify a size. So this is going to be the size of the output array. So for example, if we want to randomly pick 12 choices, we've got the following choices. Notice that some of the values have occurred multiple times, and this is because replace is set to true by default. If I override this and set replace to be false, notice that I've essentially picked a unique value from the array every time. Notice if I have replace set to false and I use a size greater than the size of the original array, I'm going to get this value error. So I can use the size of a higher order array to get a matrix. So most of the remaining functions in the numpy random module are essentially used to select a random number from a sort of distribution. So for example, we've got random integer, which can be used to select a random integer. So here we need to select a lower bound and a higher bound, and we're inclusive of the lower bound and exclusive of the higher bound. So here we can view the results in the variable explorer, and just so we can view the distribution, we can plot it as a histogram. So we see we've essentially got randomly produced integers from within the specified range, and we've got a large number of these. We've also got random.uniform, which is going to return a float. So from a lower bound to a higher bound. So in this case, the default step's essentially going to be the float precision, and we're just going to be shy of 11.0. We've also got random sample, which is essentially uniform with low set to 0 and high set to 1. We've also got triangular distribution, so here we can set the left value to be 3, the mode to be 4, and the right value to be 5, so this gives this form of triangle. If instead we set left to 3, mode to 3, and right to 5, then we're going to get a slightly different type of triangle. So we've also got the random normal, which has a location and a scale. So essentially you're going to be centered around a location, and the scale is essentially the standard deviation around the location. The standard normal essentially has the location of 0, i.e. the origin. We've also got the exponential. So here we can set a scale. And if we just view the y-axis in log, we can see that this is an exponential. And the scale is essentially how fast it's going to drop over the x-axis. So here we can change the scale from 0.1 to 10. The standard exponential essentially has a scale of 1. So here the scale is going to be e. So we've also got the Rayleigh distribution. So here I'm just going to set the scale to 1 and view what it looks like. We've also got the binomial distribution. So here I'm going to set n to be 100 and p to be 0.1. Let's update p to 0.2 and 1.0. So here we can see that the center value changes, so it's essentially 100 times 0.1, 100 times 0.2, and 100 times 1. We can also have a look at the Poisson distribution. So here I'm just going to set lambda to be 1 and lambda to be 4 and lambda to be 10. So you can see the effect of lambda. So we're essentially centered around the lambda value, but it becomes more Gaussian as lambda increases. We've also got the gamma distribution. So here I'm just going to change the shape and leave the scale as 5. So visually we can just see the changes in the gamma distribution as we increase the shape. So I don't want to dwell too much into the mathematics behind the distributions. I just plotted these out just so you could get some basic intuition to what the actual distributions look like. And if you need to use these distributions, for example, to model some data, then you'll need to review the statistics behind the distribution. NumPy has its own datetime64 class and timedelta64 class that are more accurate than the builtins, datetime, and timedelta classes respectively. So to instantiate datetime64 class, we typically use a timestamp, and we can have an accuracy down to a nanosecond. So here we've got years, months, days, and then the time, hours, minutes, seconds, and then we've got the accuracy down to a nanosecond. So in other words, we've got the general form, year, 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 month, month, day, day, and then we've got hour, hour, minute, minute, second, second, and then this is going to be nanoseconds. So the numpy implementations datetime 64 and time delta 64 aren't fully supported on the variable explorer. So if I assign this to a variable, notice it actually displays on the variable explorer, but in order to view what it is, I need to actually double click into it. Okay, so a time delta is essentially a time difference. So we can use the subtract operator to subtract one date time from another date time, and this is going to return a numpy time delta instance. So notice here it's returned 31, capital D, and that's D for days. So we can assign this to a variable, and once again we see that the variable is not fully supported in the variable explorer. So let's just change the accuracy of one of the date times, and now notice that the time delta 64 returned is returned with an hour unit, and if we expand this to minutes, then we get minutes. If we expand it to seconds, then we get seconds. If we expand it to milliseconds, then we get milliseconds. If we expand it to microseconds, then we get microseconds. And if we expand it to nanoseconds, then we get nanoseconds. So we can construct numpy.timedelta64 using a similar manner to what we've seen in the IPython console. So it might be more convenient to express this using several time delta 64 instances, for example a day instance, an hour instance, and a minute instance. And notice that the value shown in the IPython console is using the lowest unit, which is going to be minutes. So we can expand this, and I'm just going to type this over a new line. So here we're going to go down to milliseconds, and let's just go down to microseconds and nanoseconds. So here we can see that the time delta 64 expressed is in nanoseconds. So the numpy function linspace doesn't work with datetime 64 instances. So what's actually going to happen when you attempt to use this function is it's going to attempt to use division here, which isn't supported for a datetime 64 instance. So this is essentially why we get an error when we attempt to use linspace. So linspace isn't supported, but array range is supported. So here we've got a start datetime 64 instance, and we've got a stop datetime 64 instance, and then we've got a step. So the step should be a time delta 64. So for example, we're going to specify this as 1 day. So recall that we're inclusive of the start bound and exclusive of the stop bound. So if we want to include the stop bound, we need to add the step to it. Now if I assign this to a variable, notice that it's not fully supported by the variable explorer, but we can view the results in the IPython console. So we can also use array range with time delta 64 instances. So here we're going to start at 1 second, end at 10 seconds, and we're going to just add a step of 1 second here to be inclusive of the stop bound, and we're going to have a step of 1 second. So once again, this time delta 64 array isn't fully supported. However, we can view it in the IPython console. So the date time and time delta classes are more typically used within a pandas series, and this has more support in Spyder's variable explorer. The linear algebra module compartmentalizes identifiers related to linear algebra. So we can have a look at the directory of this module, and we can ask ChatGPT for more details about each of the identifiers. So if we have the following vector, we can normalize this vector using the normalize function. So if we think of this vector as a triangle, we've got 3 squared plus 4 squared, and if we take the square root of this, then we get 5. So that's how this triangle is normalized. So essentially we're just going to be squaring everything in the array and then taking the square root. So this will also work on higher order arrays, essentially just flattening the array, squaring all the terms, summing them up and taking the square root. So here it's 1 squared plus 2 squared plus 3 squared plus 4 squared. And then we take the square root of this, and we get the same result. So let me just clear out my namespace. And now what I'm going to do is I'm going to create a row, and I'm going to create a column. So once again, I'm going to use numpy.newAxis to make it clear that I'm creating a row and a column respectively. So let's open up the row and the column in the variable explorer and have a look at them side by side. Let's have a look at the shape of each of these. So here we see the inner dimensions match. So this means we can perform matrix multiplication, and this gives the value 11. So here what we've done is we've done 3 times 1 plus 4 times 2, and that gives us 11. And notice that the dimensions are the outer dimensions, so this is 1 by 1. So generally when performing array multiplication, you're going to want to make sure you're explicitly using a row or column if instead of a 1D ND array. There is the numpy function inner, which can be used to calculate the inner array multiplication of 2 1D arrays. Let's swap these around now, and let's have a look at the column shape and the row shape. So once again, we see the inner dimensions match, and array multiplication is allowed, and this will return a matrix with the outer dimensions, so 2 by 2. So here what we're doing is 1 times 3, and then 1 times 4, and then 2 times 3, and then 2 times 4. So now we've got a 2 by 2 array. So once again, it's recommended to explicitly specify a column and a row, although there is the numpy function outer, which can be used to perform this operation on 2 1D arrays. So next we can have a look at the determinant of a square matrix. So what this essentially does is it multiplies all the values in the diagonal and then subtracts all the values in the anti-diagonal. So this is going to be 6 times 4 minus 3 times 8, and this is going to be 0. So this is the equivalent of 3x plus 4y and 6x plus 8y. So basically if we take a factor of 2, then we've essentially got the same data. And in order to solve a system of equations, we need unique equations, not an equation that's duplicate of another equation, just multiplied by 2. So let's have a look at another square matrix that this time has 2 separate equations. And so we've got this set of equations and they lead to some results. So this can be 5x plus 6y equals 83. So we know if we perform array multiplication between the matrix and some coefficients, we're going to get these results. So then the question becomes, what are these coefficients? So if we go into the linear algebra module, we've got the inverse matrix. And this is only calculatable if there is an inverse. So in this case, we've got the inverse matrix. So let's perform matrix multiplication with the matrix and its inverse matrix. So notice that we've essentially got 1 across the diagonal and 0s elsewhere. And it doesn't matter what way we perform the array multiplication. In both cases, we're getting 1s across the diagonals and 0s elsewhere. And this is known as the identity matrix. So we've got the identity function and also the I function, which can be used to create an identity matrix. The I function can be used to create a non-square matrix, but it's very rare to do this. So now we know we've got essentially the identity matrix array multiplied by the coefficients. But notice what happens when you multiply coefficients by the identity matrix. They are unchanged. So now we can calculate the coefficients using the inverse matrix and the results. So this is the values of the coefficients. And we can also solve this directly using the solve function. So in this case, we just supply the matrix and the results, and we get the coefficients. So we've covered the basics of numpy, so you should now be able to follow the numpy documentation. Scipy is scientific Python, and it's essentially an extended version of numpy with a large number of scientific functions. So let me just go to the folder where numpy is installed. So we've got the site packages and we've got numpy. So here we've got the initialization script file. Notice we've got the random and linear algebra folders. We've also got some other specialized modules such as polynomial and Fourier transforms. So if we take random as an example, we generally don't type from numpy import random. And this is because there is a naming conflict with the standard module random. So normally we would access identifiers from numpy.random and then dot. We've also got the module linear algebra, and normally we would access this from the numpy namespace. If we import scipy, it's essentially an extended version of numpy. So it's got its own linear algebra module, which has more identifiers in it than the numpy equivalent. Because scipy is tailored towards scientific purposes. Scipy has an input-output module, This typically isn't imported directly, and identifiers are accessed from scipy.input-output, so there's no confusion with the standard module input-output. So the identifiers in scipy are compartmentalized into specific modules, and most of these identifiers are specialized for some sort of scientific purpose. So in order to understand these identifiers, you're going to need to have some specific training in physics, maths, or engineering classes, and you're going to be using the specific identifiers that are applicable to your subject area. And at this point, I think this is a good time to finish off this tutorial video. So we've covered essentially the basics of numpy, and just briefly mentioned that we can supplement the basics of numpy with specialized functions in scipy.